So part 5 of complex analysis practice final exam, number 12, last problem. Integrating from 0 to infinity, log x over x squared plus 2x plus 2 dx. Use a keyhole contour or another rigorous complex analytic method. Okay, so advanced residue computation. All right, so completing the square, x squared plus 2x plus 2 equals the quantity x plus 1 squared plus 1. And then if we factor this, x squared plus 2x plus 2, that equals x plus 1 minus 1 times x plus 1 plus 1. So our poles are going to be at z equals negative 1 plus 1, negative 1 plus I, and z equals negative 1 minus I. We could let x equal 1 over t, and dx dt is negative 1 over t squared dt. Then x squared plus 2x plus 2 is 1 over t squared plus 2 over t plus 2. So combining those, we're going to get 1 plus 2t plus 2t squared over t squared. And log x equals log of 1 over t. That equals negative log t. I is going to equal the integral from infinity to 0 of that log t over 1 plus 2t plus 2t squared dt. So that's going to equal the negative integral from 0 to infinity. Log t over 2t squared plus 2t plus 1 dt. So also using the parameter integral, f of a equals the integral from 0 to infinity x to the a minus 1 over x squared plus 2x plus 2 dx. Then we could say I equals f prime of 1. X squared plus 2x plus 2 equals x plus alpha times x plus beta. Where alpha is 1 minus I and beta is 1 plus I. So 1 over x plus alpha times x plus beta is 1 over beta minus alpha times the quantity 1 over x plus alpha minus 1 over x plus beta. And beta minus alpha is 2I. So f of a equals 1 over 2I, bracket, integral 0 to infinity of that x to the a minus 1 over x plus alpha dx minus the integral of 0 to infinity x to the a minus 1 over x plus beta dx, closed bracket. And using here this integral from 0 to infinity x to the a minus 1 over x plus c dx, that's going to be equal to c to the a minus 1 times pi over sine pi a. And it's initially valid for 0 is less than a is less than 1. And extended analytically, f of a equals pi over 2I sine of pi a times the quantity here, alpha to the a minus 1 minus beta to the a minus 1. And building on that, so alpha equals square root of 2 e to the negative I pi over 4. And beta, that's going to equal square root of 2 e to the I pi over 4. So alpha to the a minus 1 minus beta to the a minus 1 is going to be equal to square root of 2 to the a minus 1 times the quantity e to the negative I a minus 1 pi divided by 4 minus e to the I times a minus 1 times pi, all divided by 4 here, in that exponent, close parentheses. That equals negative 2I times square root of 2 to the a minus 1 times sine of the quantity a minus 1 pi over 4. So here for f of a, that equals negative pi, the square root of 2 to the a minus 1, sine of a minus 1 pi over 4 over sine pi a. So let a equals 1 plus h, then f of 1 plus h equals negative pi times the square root of 2 to the h sine of pi h over 4 divided by sine of pi plus pi h. And since sine of pi plus pi h equals negative sine of pi h, we're going to get f of 1 plus h equals pi times square root of 2 to the h sine of pi h over 4 divided by sine of pi h. And as h approaches infinity, f of 1 equals pi times 1/4, which is pi over 4. So log f 1 plus h equals log pi plus h log square root of 2 plus log sine of pi h over 4 minus log sine pi h. And the singular logarithmic terms cancel, and near h equals 0, ddh log f of 1 plus h, that equals log square root of 2 plus pi over 4 cotangent pi h over 4 minus pi cotangent pi h. If we substitute now cotangent equaling the following, then pi over 4 cotangent pi h over 4 minus pi cotangent pi h, that approaches 0. And from there, f prime of 1 equals f of 1 log square root of 2, and I equals f prime of 1 equals pi over 4 log square root of 2. And since log square root of 2 is 1/2 log 2, then this integral from 0 to infinity, log x divided by x squared plus 2x plus 2 dx, that equals pi over 8 times log 2. So we wind up with pi over 8 times log 2. Okay, so that's all for this practice exam in complex analysis. Thank you very much and have a great day.